IMF stands for, hi everybody, welcome back. That's not what it stands for. This is lesson 8, and it's for those of you that went home because you're scaredy cats. So, IMFs are intermolecular forces, and they are not bonds. So, they're not between atoms, okay? This is a bond, the stick, between atoms. An IMF is a force that makes this molecule love this molecule. Okay? They love each other. And what attracts them to each other is called an intermolecular force of attraction. Okay? So these are attractions between molecules, not inside of a molecule. Okay? Make sense? All right. So they are forces. I don't like this. Get rid of that hold. I'm just changing all the word. Between full molecules. They are not bonds between atoms. What they are forces between molecules. Okay? They're weaker than bonds. And they exist in the solid and liquid phase. Where are they stronger, the solid phase or the liquid phase? So generally, the solid phase has the strongest IMFs, and the gas phase has none, or at least weak IMFs. Okay, so we talk about IMFs in the solid and liquid phase. There's a relationship between the strength of the IMF and the boiling point. Boiling point, remember, is the temperature that a substance changes into a gas. And that means any substance in the container. So let's pretend we have a couple molecules and they really, 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 really love each other. Okay? Let's pretend you have a couple molecules, and if they really love each other, what would you say their forces of attraction are? Strong or weak? Strong. They're super strongly attracted to each other. Okay? So let's say me and Alexia here. We're really strongly attracted to each other in the liquid phase. Wherever she goes, I go. We're really attracted to each other. We're like two peas in a pod. We like float around the container. Okay? How are you going to get us to separate? How will you get us to separate so that I become a gas? Heat. A lot of heat or a little bit of heat? A bunch, because we really love each other. So if you want me to leave her and become a gas molecule with no forces of attraction, you have to put in a lot of heat. Okay? But now let's say, if, Alexia, she's all right. I kind of like her, sort of. Like, I'll talk to her if I have nothing better to do. You hear me? We're only weakly attracted to each other, I don't know, I might be looking at that molecule over there because they're kind of cute too. Is it going to take a lot of energy to separate us? Now we only have weak IMFs. See them? Right? Just a little bit of heat, and I'm out the door. Right? I'm becoming a gas. So, the stronger the IMFs, the more the molecules love each other, the higher the boiling point. You have to put a lot more heat in to separate them and turn it into a gas. But the weaker the forces of attraction, the less energy you have to put in, the lower the boiling point would be. Okay? So the stronger forces of attraction, the higher the boiling point. Before we move on, I have a question for you, and everybody at home, you can play along too. Carbon dioxide versus water. My question is, who has the stronger IMFs? Who has the stronger forces of attraction? Okay, so my question is carbon dioxide versus water. Who has has the stronger IMFs? And Kevin, you had a question? It is. It is whoever's boiling point is higher. That's exactly how you do it. Stronger IMFs is the one with the higher boiling point.
Are you really recording this?
Yeah.
Yes. Hi, Mom.
You want record of Kevin giving the right answer? Is that what it is? This
Yeah.
day really doesn't happen. It is kind of
Let's
serendipitous.
say hi to Mom.
Okay. Yeah, you can say hi to your mom. Go ahead.
Hi, Mom. My
From-
mom watches your videos.
From?
Oh.
From Zach.
Okay. All right. Now you have to go home and show it. So the stronger the IMFs, the higher the boiling point, right? So who has the stronger IMFs here? Water. Water's boiling point is about 100 degrees Celsius, right? Right now, that's the faucet turning on. At this temperature, water is a liquid, right? But what's carbon dioxide right now? It's a gas. You're exhaling it. Carbon dioxide has already boiled at this temperature. I don't know what its boiling point is. We have to look it up. But it's already boiled right now at this temperature. So carbon dioxide has a lower boiling point. Water has a higher, oh boy, higher boiling point. And so this has stronger IMFs. And we know that because this is a liquid right now and this is a gas. Okay? So that's the general stuff you got to know about IMFs. Now, there's 4 specific IMFs you need to know. The first one is called a dipole-dipole force of attraction. Oops. Dipole-dipole force of attraction. And all that it is, don't panic. All that it is an attraction between molecules that are polar. Give me an example of a polar molecule. Pick one. I don't care. H2O is polar. H2O will have dipole-dipole forces. Is HF polar? Yep. HF will have dipole-dipole forces of attraction. Is HCl polar? Yes, right? This could be your H. This could be your Cl. This could be your H. This could be your Cl. And all the and remember, to mean polar means that you have partial charges. The one with the higher electronegativity gets the negative. The one with the lower electronegativity gets the positive. And so isn't it entirely possible that if we have these polar molecules where one side's positive and one side's negative, that since opposites attract, you could get an attraction between this positive H up here and this Cl on a whole nother molecule because opposites attract? You sure could, right? Could you get an attraction here? No, but this could flip and you could get an attraction there. So I want you to draw these dotted lines that I'm drawing so that you can see those are your dipole-dipole forces. It's an attraction between this dipole, dipole A, and this dipole, dipole B. That's what a dipole-dipole force is. It's an attraction between 2 different polar molecules. But the positive of one is attracted to the negative of another. That's it. That's all it is. And that makes sense because opposites attract. And so if they're really attracted, they'll be close together, they'll love each other a lot, they'll be hard to boil. Okay? Hard to separate. They'll have high boiling points. A really special kind of dipole-dipole is here. It's called a hydrogen bond. Not anyone with hydrogen can make a hydrogen bond. Okay? So, for example, in this last picture that I drew with the HCl, there ain't no hydrogen bonds there. Just having H doesn't mean you have a hydrogen bond. Okay? So what is a hydrogen bond? A hydrogen bond is when the H of one polar molecule that's positively charged is attracted to the negative charge on another polar molecule. But this negative has to be a special negative. It can only be O, F, or N because they're small and they have a really high electronegativity. So it's really just like the last example. It's a dipole-dipole force with polar molecules, but it's a special circumstance. The other element is either going to be O, F, or N with the H. Okay? O, F, or N. Those are the only ones that make hydrogen bonds. I should mention, see where I'm writing on your thing? This bond, that's not a hydrogen bond. A hydrogen bond is not something bonded to H. This is not a hydrogen bond. I think that's worth labeling. This is not a hydrogen bond. That is a polar covalent bond. That is two different nonmetals. That's polar covalent. That's what it is, right there. Okay, the hydrogen bond is this red one. This is your hydrogen bond, when the H of one is attracted to the O, F, or N of another. Okay? So these are an especially strong type of dipole-dipole interaction. They are attractions between the positive hydrogen of one molecule and the atom with the partial negative charge on another molecule. But I want to put an asterisk here. Not just any old negative. The negative must be, and we'll just draw an arrow down here, O, F, or N. You know how I remember them? I think of them often. Often. OFN. Often. Often. And they are fun, aren't they? Those hydrogen bonds, they sure are fun. And I heard Brandon say a minute ago, he's had quite enough of hydrogen bonds. Haven't you? Enough. Quite enough of them. So why these ones? Why O, F, and N? And that's a question that comes up quite frequently. Why does oxygen, or do oxygen and hydrogen, fluorine and hydrogen, and nitrogen and hydrogen make hydrogen bonds, but chlorine and hydrogen don't? How come there's no hydrogen bond here? There's a dipole-dipole, but there's no hydrogen bond. And that's because chlorine's too fat. It's too big. Hydrogen bonds are only made between...
Good afternoon, Niagara Falls High School. Please excuse the interruption. They just have a short announcement. All Niagara Falls High School varsity girls basketball players must report to the main gym by 4:15. All varsity girls basketball players report by 4:15 to the main gym. Thank you.
They're small and they're highly electronegative. Chlorine's too big and it doesn't have a high enough electronegativity. That's why it doesn't make a hydrogen bond. But I gotta tell you, these guys sunk the Titanic, these hydrogen bonds. Because what phase of matter is the most dense? Solid, liquid, gas? Mostly, not water. Why does ice float? Ice is solid water because it's less dense than liquid water. In most things in nature, the solid phase of a substance is more dense, the molecules are closer together, than the liquid phase, than the gas phase. The gas phase, they're all spread out. But in water, when the water is liquid and the molecules are free to move, more hydrogen bonds can form, which makes liquid water more dense than solid water, which is why ice floats, which is why there are icebergs, which is why the Titanic sunk. So hydrogen bonds are responsible for the sinking of the Titanic. Blame it on the hydrogen bonds. Yeah, go. It does. Yes, it does. Well, how would you know if it was floating? If it's just shoved in there. I'd say put less ice in. And if you pour the water in, it comes to the surface.
Okay, so you have a flat tank that's all filled with ice.
Okay.
You pour the water in there so that it goes out in the cracks.
It's because you have too much ice in there.
It's gonna flow to the top of the water.
It can't float to the top of the water because there's not enough water. Okay. All right.
Oh my.
I hope that's the right answer. So here's the other thing that these hydrogen bonds, if it weren't for these hydrogen bonds, which are an unusually strong type of IMF, I don't think we have that written anywhere, but they're pretty strong type of IMF. In fact, they're the strongest type of IMFs that we'll be dealing with. Water would actually be a gas at this temperature because other things like H2S, S is right below O. It's the same exact structure. 2 lone pairs, the whole bend. That does not have hydrogen bonds because it's S, right? It's too big and too ugly to make hydrogen bonds. It's a gas at this temperature. It's what's, if you ever smelled rotten eggs, that's hydrogen sulfide gas. So water, which is exactly the same except an O for an S, is liquid at this temperature, but that's a gas. So if it weren't for these hydrogen bonds existing, A, the Titanic never would have sunk, but B, there would be no liquid water on planet Earth. It would exist as a gas at this temperature. And so you couldn't go get a drink of water. You couldn't be mostly water in your body because it wouldn't exist. So life on planet Earth really wouldn't exist without hydrogen bonds. Also, you know in DNA how you have bases that pair A to T, C to G? What holds the A to the T and the C to the G to make your DNA double-stranded is hydrogen bonds. They connect through hydrogen bonds. So hydrogen bonds are super important, and they give water its unusually high boiling point for covalent things. And we're just going to qualify this compared to other covalent things. Because water's boiling point certainly isn't high if you compare it to salt, right? But it's high compared to other things that are covalent. Okay, we have 2 types of IMFs to talk about, which we'll finish tomorrow. We'll do some practice with this. And remember, we're going to have a test on Thursday, so just keep thinking about science. If you're here in my room right now, you don't have any homework. If you're at home, hopefully your homework's done. And we will see you tomorrow, everybody. Have a great night. Bye-bye. Anybody want to say goodbye?
Stay classy.
Stay classy, San Francisco, San Diego.
Wow, you